Right now, as you watch this, something ancient is hurtling toward our sundial. It's been traveling for longer than human civilization has existed, falling through the darkness from the edge of our solar system. Within days, it will reach the most critical point of its journey, a moment astronomers call perihelion, the closest approach to our star. What happens next will be spectacular. This visitor from the cosmic deep carries ice older than the pyramids, older than the first humans who looked up at the night sky and wondered what those moving lights could be. For millions of years, it drifted in frozen silence, waiting. Then something disturbed its rest, perhaps the gravitational whisper of a passing star, or the subtle tug of the Milky Way's tides. Whatever the cause, it began to fall sunward, accelerating through the void, racing toward a rendezvous with light and heat. On the 20th of January 2026, Comet Wierzchos will swing around the Sun at its closest point. Ancient ice will meet solar fury. The transformation will be dramatic. You might be wondering why this matters. After all, comets have been visiting our neighborhood for billions of years. But here's what makes this particular moment fascinating. Every comet is different, and each one carries secrets from the birth of our solar system. When Comet Wierzchos was formed, the planets were still taking shape. The ice locked inside this wanderer preserves materials from that ancient era, frozen in time, unchanged for eons. Now, as it approaches the Sun, that ice will sublimate directly into gas, releasing those primordial substances into space where our instruments can analyze them. We're watching a time capsule open. Let me tell you what you're about to discover in the next hour. We'll trace the journey of this remarkable visitor from the moment astronomers first spotted it in March 2024 to its dramatic solar encounter happening right now. You'll learn where comets like this one come from, a region so distant and cold it makes Antarctica look tropical. We'll explore what happens when ancient ice encounters the full force of solar radiation, a transformation that turns a frozen rock into a glowing spectacle millions of miles long. You'll discover why scientists care so deeply about these icy messengers, and what they can teach us about the origins of everything, including the water in your body and the air you breathe. By the time we reach the end of this journey together, you'll understand why comets have fascinated humanity for thousands of years, and why each new visitor deserves our attention. You'll know what makes Comet Wierzchos special among the thousands of comets we've catalogued. And you'll have the knowledge to appreciate what's unfolding in our skies right now, even if you can't see it with your own eyes. But before we dive into that story, I want to ask you something. Have you ever seen a comet with your own eyes? Maybe you caught Hale Bopp back in 1997, or NEOWISE during the pandemic summer of 2020. Perhaps you remember your parents or grandparents talking about comets they saw decades ago. Drop a comment and share your experience. And if you're as fascinated by these cosmic visitors as I am, subscribe so we can explore more of these stories together. The universe is full of wonders, and I want to share them with you. Now, let's talk about why Comet Wierzchos matters in particular. This isn't the brightest comet ever observed. It won't be easily visible to the naked eye, and you won't see it dominating the twilight sky like some of history's great comets. But what it lacks in visual spectacle, it makes up for in scientific value and in the remarkable story of its discovery. Every comet has a story, and this one begins in the desert mountains of Arizona, at an observatory where dedicated astronomers spend their nights searching the darkness for moving objects. Most nights, they find asteroids' rocky fragments orbiting between Mars and Jupiter, but occasionally they discover something more special. They find ice. When astronomers discovered this particular visitor in March 2024, they noticed something immediately intriguing. This wasn't just another space rock. Telescopic images showed a fuzzy appearance around the central point of light, a coma, astronomers call it, the cloud of gas and dust that forms when ice begins to sublimate in sunlight. And stretching away from that fuzzy glow, pointing away from the sun, like a cosmic weather vane, was a faint tail. This was a comet, fresh from the outer reaches, beginning its transformation. The discovery set off a cascade of observations. Astronomers around the world turned their instruments toward this new visitor, tracking its motion, measuring its brightness, analyzing the light reflecting off its surface and shining through its coma. Each observation added another piece to the puzzle. Where did it come from? How close would it pass to the sun? Would it become bright enough for amateur astronomers to see? And most importantly, what secrets might it reveal? As the data accumulated, the picture became clearer. This comet was on what astronomers call a long-period orbit, meaning it takes thousands or perhaps even millions of years to complete one trip around the Sunday. It came from a region we can barely observe, a vast spherical cloud of icy objects surrounding our entire solar system at an incredible distance. This was a visitor from the frontier of our cosmic neighborhood, the boundary between what belongs to the sun and what belongs to interstellar space. And here's the remarkable part. This might be the only time in human history that we ever see this particular comet. After it swings around the Sun and begins its outward journey, calculations suggest it might never return. The gravitational interactions during its passage through the inner solar system could change its orbit just enough to fling it out into the galaxy forever. This is possibly a once-seen-forever event. That's why scientists have been so interested. That's why observatories around the world have been tracking its progress. And that's why, on the 20th of January 2026, as this ancient wanderer reaches perihelion, dozens of telescopes will be watching, including some of the most sophisticated instruments humanity has ever built. We're not just watching a pretty light show, we're witnessing something far more profound. We're watching a piece of the ancient solar system reveal itself, however briefly, before returning to darkness. We're seeing materials that formed before Earth existed, before life began, before anything we know came to be. In a very real sense, we're looking at the ingredients from which everything in our solar system, including ourselves, was built. So this is the moment we're in. Right now, as you sit there, Comet Wierzchos is racing toward the Sun, heating up, becoming more active with each passing hour. The ice that has remained frozen for eons is beginning to boil away into space. The comet is brightening, growing more active, approaching its moment of maximum transformation. In days, it will round the Sun and begin its long journey back to the outer darkness. We have this brief window to observe, to study, to appreciate what's happening, and that's exactly what we're going to do together in this video. We're going to follow the complete journey of this remarkable visitor, from discovery to perihelion to its eventual departure from our neighborhood. We're going to understand what makes comets so special, so scientifically valuable, so worthy of our attention and wonder. The story of Comet Wierzchos is ultimately a story about time, distance, and transformation. It's about objects that preserve ancient history, about journeys that span unimaginable reaches of space, and about the spectacular changes that happen when frozen materials from the outer darkness encounter the heat and light of our Sunday. It's a story that connects us to the deepest history of our solar system and reminds us that we live in a dynamic, changing, remarkable cosmic neighborhood. Let's begin at the beginning, with the moment of discovery, when one dedicated astronomer noticed something unusual moving through the constellation Draco. March 2024 was an ordinary month at the Mount Lemmon Observatory in Arizona, right up until it wasn't. The observatory sits high in the Santa Catalina Mountains, above much of the atmospheric turbulence that plagues lower-altitude telescopes. On clear nights, the sky there is exceptional dark, steady, perfect for searching the heavens for moving objects. Kacper Wierzchos knows that sky intimately. As part of the Catalina Sky Survey team, he spends his nights doing something that requires both technical skill and remarkable patience: comet hunting. Most of what he finds are asteroids, the rocky debris left over from the solar system's formation. But every so often, maybe a few times a year if you're lucky, you spot something different. You find a moving object that looks fuzzy rather than sharp, that shows signs of activity, that betrays the presence of ice. The work is methodical. The telescope takes multiple images of the same patch of sky over the course of several hours. Computers compare those images, looking for anything that moved between frames. Most of the candidates are quickly identified known asteroids, satellites, even cosmic rays hitting the detector that create false signals. But occasionally, something shows up that doesn't match anything in the database. That's when the real work begins. On the night of the discovery, Wierzchos was examining images of a region in the constellation Draco, the dragon that winds between the Big and Little Dippers. The images showed a faint object moving against the background stars. That alone wasn't unusual, but when he looked closer, he noticed something that made him pause. The object wasn't a sharp point of light, like an asteroid. It had a slightly fuzzy appearance, as though surrounded by a haze, and extending from that fuzzy center was a faint streak, barely visible, pointing away from the direction of the Sunday. Experienced comet hunters know that feeling. The moment when you think you might have found something special, but you don't celebrate yet, you confirm. Wierzchos immediately requested follow-up observations. Other telescopes, other observers, needed to see this object, to verify it was real, and to gather more data about its motion and appearance. The confirmation came within hours. Yes, this was a comet. Yes, it showed clear cometary activity, the coma and tail that distinguish comets from inert rocky bodies. And yes, it was a new discovery, not a previously known comet returning for another visit. The object was officially designated as a comet, and following the tradition that dates back centuries, it bore the name of its discoverer, Comet Wierzchos. But finding a comet is just the first step. What astronomers really want to know is where it came from and where it's going. That requires careful tracking over multiple nights to plot the orbit with precision. As observatories around the world contributed their observations, a picture began to emerge. The orbit was extraordinary. This wasn't a short-period comet like Hale, which returns every 75 years or so, familiar to humanity across generations. This was a long-period visitor, an object on an orbit so elongated that it might take tens of thousands of years to complete one circuit, if it completes one at all. The calculations suggested this comet came from the Oort Cloud, that distant reservoir of icy bodies at the very edge of the Sun's gravitational influence. Even more intriguing were the predictions about its closest approach to the Sunday. The numbers indicated perihelion would occur in January 2026, less than 2 years after discovery, and the perihelion distance would bring the comet quite close to the Sun, close enough to experience intense heating, close enough to potentially put on a spectacular display. Initial brightness estimates generated excitement. Could this become a comet easily visible to the naked eye? Would it develop the kind of long, dramatic tail that captures public imagination? The possibilities seemed promising, and word began to spread through the astronomical community. Observing proposals were written. Telescope time was requested. Scientists planned observation campaigns. Wierzchos and his team continued their monitoring through the spring and summer of 2024. Each observation added to the understanding of this new visitor. The comet was showing steady activity, developing a healthy coma as sunlight continued to warm its surface. The tail was growing more prominent. Everything suggested this comet was behaving well, responding to solar heating as expected, becoming more active as it approached the inner solar system. By late 2024, dozens of observatories were tracking Comet Wierzchos. Amateur astronomers with backyard telescopes joined the effort, contributing their observations to international databases. The comet had become a target of global interest, one of those objects that brings the astronomical community together in shared study. But as more data accumulated, the brightness predictions began to change. The comet wasn't brightening quite as rapidly as the optimistic initial estimates suggested. It became clear that while Comet Wierzchos would be a fine object for telescopes, it wouldn't become a spectacular naked-eye comet dominating twilight skies. Some disappointment rippled through the community, especially among those hoping for a repeat of recent great comets like NEOWISE. Yet the scientific community remained deeply interested. A comet doesn't have to be spectacularly bright to be scientifically valuable. What matters is accessibility for study, and Comet Wierzchos would certainly provide that. Its orbit brought it close enough to Earth for detailed observation, while also taking it close enough to the Sun for strong activity. It was, in many ways, an ideal target for scientific investigation. In 2024, something exciting happened. The James Webb Space Telescope, the most powerful infrared observatory ever built, turned its attention to Comet Wierzchos when it was still far from the Sunday. JWST specializes in infrared light, which is perfect for studying comets because many of the gases they release, like carbon dioxide, carbon monoxide, and water vapor, emit strongly in the infrared. The observations were stunning in their detail and scientific richness. JWST detected carbon dioxide outgassing from the comet's nucleus, evidence that the ice deep inside was beginning to sublimate as solar heating penetrated the surface. The telescope also observed water vapor, along with traces of other volatile compounds. Each detection added to the chemical inventory of this ancient visitor, revealing what materials were present when the comet formed billions of years ago. The observations confirmed what many had suspected. This was a pristine comet, one making perhaps its first visit to the inner solar system. Unlike short-period comets that have been heated by the Sun many times, losing their most volatile materials over repeated visits, Comet Wierzchos still contained the full complement of original ices. It was as fresh a sample of ancient solar system material as astronomers could hope to study. Throughout 2025, the comet continued its inward journey. Month by month, it crept closer to the Sun, growing steadily more active. Observers tracked the development of gas jets erupting from specific locations on the rotating nucleus. They measured the production rates of different molecules. They watched the dust tail grow longer and more structured, shaped by the pressure of sunlight pushing on microscopic particles. Professional and amateur astronomers coordinated their efforts, creating a comprehensive observation campaign. Every few nights, somewhere in the world, someone was watching Comet Wierzchos, adding to the growing body of knowledge about this visitor. The international collaboration exemplified the best of astronomical community work, people across continents working together, sharing data freely, all focused on understanding this one remarkable object. By late 2025, as the comet approached the inner solar system, anticipation built for the perihelion event. This would be the climax of the comet's journey, the moment of maximum heating and activity. Whatever happened in those hours around closest approach would tell scientists volumes about the structure and composition of this ancient wanderer. Observing plans were finalized, instruments were prepared. The countdown to perihelion began. And that brings us to now, to January 2026, to these critical days as Comet Wierzchos makes its closest approach to our star. The discovery phase is complete. The monitoring phase is reaching its culmination. Now comes the main event, the moment everything has been building towards since Kacper Wierzchos first noticed that fuzzy, moving object in March 2024. But to fully appreciate what's about to happen, we need to understand where this comet came from and what kind of journey brought it here. Imagine standing on Earth and looking up at the night sky. The moon is about 240,000 miles away, visible and familiar. The sun sits 93 million miles distant, close enough that its light reaches us in just over 8 minutes. Even Neptune, the most distant planet, orbits about 2.8 billion miles from the sun, far but still within what we think of as our solar system proper. Now multiply that Neptune distance by 1,000, then multiply it again by another factor of 10. You're approaching the region where Comet Wierzchos spent most of its existence, the Oort Cloud, a vast spherical shell of icy objects surrounding our entire solar system at a distance so extreme it challenges comprehension. The Oort Cloud begins somewhere around 1 trillion miles from the sun and extends perhaps 2 or 3 trillion miles farther out. At those distances, the sun appears as little more than a bright star among the other stars, providing almost no heat. The temperature hovers just a few degrees above absolute zero, the coldest temperature possible. In that frozen darkness, billions upon billions of icy bodies drift in lonely orbit, barely moving, barely changing, waiting. These objects formed during the birth of our solar system, about 4.5 billion years ago. Back then, a vast cloud of gas and dust was collapsing under its own gravity, spinning faster as it shrank, flattening into a disk with a hot, dense center that would become our Sunday. Throughout that disk, materials were condensing, sticking together, growing from dust, grains, into pebbles, into rocks, into boulders, into objects, massive enough that their own gravity pulled them into spheres. Close to the forming sun, where temperatures were high, only rock and metal could remain solid. That's where the rocky planets formed Mercury, Venus, Earth, and Mars. Farther out, beyond what astronomers call the frost line, it was cold enough for water to freeze. There, ice could exist alongside rock, and the giant planets Jupiter, Saturn, Uranus, and Neptune grew massive by accumulating not just rock but enormous quantities of frozen water and other ices, along with the hydrogen and helium gas that made up most of the original cloud. But the formation process was chaotic. Not everything that condensed in the outer solar system ended up in planets. Countless smaller icy bodies formed as well, comet nuclei, essentially objects ranging from less than a mile across to perhaps a few dozen miles in diameter. These objects orbited in the region where the giant planets were forming, and that's where their fate was sealed. When you have giant planets swinging around the sun, their immense gravitational fields affect everything nearby. The icy bodies in their neighborhood got pulled this way and that, their orbits perturbed, some pulled inward toward the sun, others flung outward. The inward-flung objects became short-period comets, settling into relatively stable orbits that brought them back to the inner solar system every few years or decades. But the outward-flung objects were sent on a one-way journey to the outer darkness. They didn't leave the solar system entirely. The sun's gravity, though weak at such distances, still held them in very elongated, very slow orbits. They became the Oort Cloud, a gravitationally bound reservoir of primordial icy material, a deep freeze where the original building blocks of the solar system could be preserved essentially unchanged for billions of years. There those objects remained, in frozen hibernation, circling the distant sun once every few million years. Most of them will stay there forever, never disturbed, never changing. But occasionally, something happens. A star passes relatively close to our solar system, not close enough to be dangerous, but close enough that its gravitational field gives a gentle tug to some of the distant Oort Cloud objects. Or the solar system's motion through the galaxy takes it through a slightly denser region, where the combined gravitational effects of many distant stars create a tide that disturbs the outermost comets. These perturbations are tiny, barely measurable, but at such vast distances, even small gravitational nudges can change orbit significantly. An Oort Cloud object in a stable, nearly circular orbit billions of miles from the sun suddenly finds itself on a new trajectory, one that takes it inward, falling toward the distant point of light that is our star. The journey inward takes an extraordinarily long time. Even though the object is falling toward the sun, accelerating under gravity, the distances involved are so vast that thousands or even millions of years pass during the inward plunge. For almost all of that journey, the comet remains frozen and inert, a dark, silent iceberg drifting through the void. But eventually, after ages of falling, the comet crosses into the realm of the planets. It passes Neptune's orbit, then Uranus, then Saturn. It's still far from the sun, still cold, but no longer quite as frozen as it was in the Oort Cloud. As it continues inward, crossing Jupiter's orbit and entering the inner solar system, something begins to change. Sunlight, growing stronger as the distance decreases, starts to warm the comet's surface. The nucleus, the actual solid body of the comet, is typically just a few miles across, an irregular chunk of ice mixed with dust and rocky particles. For billions of years, that ice remained solid. Now, for the first time since the comet formed, it begins to warm above the critical temperature where ice can sublimate. This is what distinguishes comets from asteroids. Asteroids are rocky or metallic bodies that formed in the warmer inner solar system or lost their volatile materials long ago. They're inert, unchanging as they orbit. But comets carry ice, and when that ice warms, it doesn't melt. There's no atmospheric pressure in space for liquid water to exist. Instead, the ice sublimates, turning directly from solid to gas, and that gas carries dust particles along with it as it streams off the nucleus into space. This process creates the coma, the fuzzy cloud of gas and dust that surrounds the comet's nucleus and can grow to be hundreds of thousands of miles across. It creates the tail, the solar radiation pressure and the solar wind, the stream of charged particles flowing out from the sun, push the gas and dust away from the nucleus, always pointing away from the sun like a cosmic windsock. The comet transforms from a dark, frozen object, invisible even to most telescopes, into a glowing, spectacular visitor that can, in some cases, become bright enough to see in daylight. All because ancient ice is finally, after billions of years, experiencing warmth. This is the journey Comet Wierzchos has made. Sometime in the distant past, perhaps hundreds of thousands or millions of years ago, something disturbed its orbit in the Oort Cloud. Maybe a star passed within a light year or two of our solar system, close enough to gravitationally nudge the distant comets. Whatever the cause, Comet Wierzchos began falling sunward, beginning a journey across an appreciable fraction of a light year, a journey that has finally brought it to our neighborhood. We don't know how many times, if ever, this particular comet has visited the inner solar system before. The observations suggest this might be its first trip, or at least one of very few trips. The comet still contains highly volatile materials like carbon dioxide that would have been lost after multiple close passes by the Sunday. This is a fresh visitor, carrying ice that has remained undisturbed since the solar system was young, and that's precisely what makes it so scientifically valuable. The materials locked in that ice are samples from the original solar nebula, the cloud of gas and dust from which everything in our solar system formed. Studying the composition of that material tells us what the building blocks were, what elements and molecules were available when the planets formed, what conditions were like in the outer solar system 4.5 billion years ago. Comets are time capsules, and long-period comets like Wierzchos are the most pristine capsules of all. They spent almost their entire existence in the deep freeze, preserved perfectly, waiting for the moment when they would fall sunward and reveal their secrets. That moment is now. That moment is happening as we speak. Comet Wierzchos, after its million-year journey from the edge of the solar system, is about to experience the closest approach to the sun it may ever have. The ancient ice is about to be tested by solar fire. The transformation didn't happen all at once. As Comet Wierzchos fell inward through the outer solar system during 2024 and 2025, the changes came gradually, building in intensity as the distance to the sun decreased. When the comet crossed Jupiter's orbit, still several hundred million miles from the sun, the first signs of activity appeared. The sunlight there is only about 4% as intense as it is at Earth's distance, but even that faint warmth was enough to begin sublimating the most volatile ices. Carbon monoxide, which can sublimate at extremely low temperatures, began turning to gas. Carbon dioxide, less volatile than carbon monoxide, but still more reactive than water ice, started to outgas as well. These early releases were subtle. The coma that formed around the nucleus was faint, visible only to sensitive telescopes. But it was real, and it marked the comet's awakening after eons of frozen dormancy. The ancient ice was responding to the sun's warmth for the first time in billions of years. As the comet continued inward, crossing Mars's orbit and approaching Earth's distance from the sun, the activity intensified. Water ice, which makes up the bulk of most comets' volatile material, began to sublimate in earnest. The sublimation process works from the outside and sunlight warms the surface layers first, and the ice there transitions directly to gas, carrying dust particles along in the flow. This creates jets, streams of gas and dust erupting from active areas on the comet's surface. Because the nucleus is rotating, these jets turn on and off as different areas face the sun and then rotate into darkness. Observers watching Comet Wierzchos noted these variations in brightness and gas production. correlating with what appeared to be a rotation period of several hours. The comet was revealing its shape and structure through the pattern of its activity. The coma grew steadily larger. By late 2025, it had expanded to perhaps 100,000 miles across. Maybe more a cloud of gas and dust surrounding the tiny nucleus, like an atmosphere, though far more tenuous than Earth's air. Within that coma, sunlight was causing chemical reactions, breaking apart molecules and creating new compounds. The coma glowed with its own light, fluorescence from excited molecules relaxing back to their ground states and emitting photons in the process. The tail developed as well, actually two tails, though they're not always easy to distinguish. The dust tail formed from the microscopic particles carried away from the nucleus by the sublimating gas. These particles, no longer held by the comet's weak gravity, felt the pressure of sunlight pushing them away from the sunday. Because dust particles have mass and inertia, they responded slowly to that pressure, and the dust tail curved, following the comet's orbital path, creating a sweeping arc across the sky. The ion tail formed from gas atoms and molecules that had been ionized by solar ultraviolet light and by interactions with the solar wind. These charged particles responded directly to the magnetic field carried by the solar wind, and the ion tail pointed exactly away from the sun like an arrow, often glowing with a distinctive blue color from carbon monoxide ions. Earlier in the comet's approach, something remarkable happened. The James Webb Space Telescope, orbiting 1,000,000 miles from Earth at the L2 Lagrange point, dedicated several hours of observation time to Comet Wierzchos in 2024. JWST's infrared sensors are perfect for studying comets, able to detect the heat from the nucleus itself and identify specific molecules by their infrared spectral signatures. The observations were scientifically rich. JWST detected strong carbon dioxide emissions, confirming that CO2 ice was sublimating actively as the comet approached perihelion. The telescope also observed water vapor, as expected, along with traces of methanol, formaldehyde, and other organic molecules. Each detection added to the chemical inventory of this ancient visitor. What particularly interested scientists was the detection of complex organic molecules compounds containing carbon and hydrogen bonded in intricate ways. These organics likely formed in the original solar nebula, or perhaps even earlier, in the interstellar cloud from which the nebula collapsed. Finding them in comets supports the theory that comets may have delivered important organic materials to the early Earth, possibly contributing to the chemistry that eventually led to life. But JWST also revealed something else. The comet was not brightening quite as dramatically as the most optimistic predictions had suggested. The observations allowed scientists to estimate the size of the nucleus more accurately and to measure how actively it was outgassing. The numbers indicated a relatively small nucleus, perhaps 2 or 3 miles across, and while it was certainly active, it wasn't producing gases at the extraordinary rates that would be needed for the comet to become a spectacular naked-eye object. Some disappointment followed this realization, especially among amateur astronomers hoping to photograph a bright comet from their backyards. But the scientific community remained enthusiastic. A comet's brightness matters for public visibility, but its scientific value comes from what we can learn about its composition and behavior. On that front, Comet Wierzchos was delivering beautifully. Through December 2025 and early January 2026, the comet continued its steady approach to perihelion. Observatories around the world maintained their monitoring campaigns. Each night's observations showed the comet growing slightly more active, slightly brighter, responding to the increasing intensity of sunlight as the distance to the sun decreased. By mid-January, the comet was approaching its most active phase. It had moved inside Earth's orbit, closer to the sun than our planet, entering a region of intense solar heating. The temperature on the sunlit side of the nucleus was climbing toward and past the freezing point of water. Ice that had remained solid for 4.5 billion years was boiling away into space at an accelerating rate. The gas production increased dramatically. Estimates suggested the comet was releasing several hundred pounds of water vapor per second, along with proportional amounts of other ices. That might not sound like much, but remember, this process would continue for days as the comet passed through perihelion. Over that period, the comet would lose thousands of tons of material, a significant fraction of its total mass. The coma expanded further, now possibly reaching several 100,000 miles in diameter. If you could somehow see the coma from Earth with the naked eye at its full extent, it would appear larger than the full moon, though of course it's far too faint and diffuse to actually be visible that way. The tail extended millions of miles through space, a river of gas and dust flowing away from the nucleus, pushed by solar radiation and the solar wind. Photographers capturing images of the comet in early January 2026 revealed intricate structures in the tail streamers and rays, where the dust wasn't distributed evenly, created by variations in the outgassing from the nucleus. These structures told a story about the comet's activity, about which areas of the surface were more active than others, about how the rotation of the nucleus created patterns in the outflow of material. But there was also some concern. As comets approach very close to the Sun, they experience tremendous stress. The side facing the Sun can heat to several hundred degrees, while the side facing away remains frozen. This thermal stress can crack the nucleus, even break it apart entirely. History is full of comets that fragmented during close solar approaches, sometimes breaking into dozens of pieces, sometimes disintegrating completely into clouds of dust. Would Comet Wierzchos survive its perihelion passage intact? That question added an element of suspense to the observations. Scientists watched carefully for any signs of fragmentation, sudden brightening or changes in the coma structure that might indicate the nucleus had broken. As of mid-January, the comet appeared to be holding together well, but the real test would come during the hours immediately around perihelion. Now, in these days leading up to January 20, the anticipation is at its peak. The comet is approaching the moment of maximum heating, maximum stress, maximum activity. Everything that has been building for nearly 2 years since discovery, and indeed for millions of years since the comet began its inward fall from the Oort Cloud, is culminating in these critical hours. The ancient ice is about to face its greatest challenge. The moment of perihelion is at hand. The 20th of January 2026, mark that date. On this day, Comet Wierzchos will reach perihelion, swinging around the Sun at its closest approach, experiencing solar heating more intense than at any other point in its long existence. This is the moment everything has been building toward, the climax of the comet's journey, the peak of its transformation from frozen wanderer to active, glowing visitor. Perihelion, from the Greek words for near and sun, represents the point in an elliptical orbit where an object comes closest to the star it's orbiting. For planets, perihelion passes unremarkably. Earth reaches perihelion every year in early January, coming about 3 million miles closer to the Sun than at its most distant point. But the difference is subtle and creates no dramatic effects. For comets, especially long-period comets making rare visits to the inner solar system, perihelion is transformative. The numbers tell part of the story. At perihelion, Comet Wierzchos will be about 53 million miles from the Sun's surface, roughly 60% of the distance from the Sun to Earth. That might sound far, but in astronomical terms, it's remarkably close. The solar radiation intensity at that distance is about 3 times stronger than what Earth receives, powerful enough to heat the sunlit side of the comet's nucleus to temperatures well above the boiling point of water. Not that water can actually boil in the vacuum of space without atmospheric pressure, liquid water can't exist at all. Instead, the ice sublimates directly into gas, skipping the liquid phase entirely. But the process is violent nonetheless. The energy from solar heating, breaking molecular bonds, liberating water molecules from the ice matrix, creating jets of gas that erupt from the nucleus at speeds of hundreds of miles per hour. What makes this moment scientifically precious is that we're watching the comet under maximum stress. The sublimation rate reaches its peak during perihelion. The comet is losing mass at its fastest rate, shedding layers of ancient ice that immediately vaporize in the intense sunlight. In those hours around closest approach, the comet will lose more material than during weeks or months farther from the sunday. It's a dramatic display of solar power, of what our star can do to a chunk of ice, even when that ice has been frozen for billions of years. The coma around the nucleus expands to its maximum extent during perihelion, fed by the peak gas production. Observations during these critical hours will reveal the true size and activity level of the nucleus, information that can be difficult to determine accurately at other times. Scientists will measure how much gas is being produced, which molecules are most abundant, how the production rate changes over the hours of perihelion passage. Every measurement adds to the scientific understanding of what this comet is made of and how it behaves under extreme conditions. The tails reach their most spectacular development as well. The dust tail, fed by the enormous quantities of dust carried away by the sublimating gas, can stretch millions of miles through space, possibly becoming more structured and dramatic as density variations in the gas outflow create streamers and fans in the dust distribution. The ion tail, responding to the intense solar wind this close to the Sun, glows more brightly, pointing exactly away from the Sun like a cosmic compass needle. But here's the challenge. Observing a comet during perihelion is difficult precisely because it's so close to the sunday. From Earth's perspective, Comet Wierzchos will be angularly near to the Sun in our sky during perihelion, making it extremely hard to observe. You can't point a telescope close to the Sun without risking damage to sensitive equipment. Observers need proper equipment and knowledge to safely view objects near the Sun in daylight. The angular separation, measured in degrees, determines what's possible. During perihelion on January 20, the comet will be roughly 15 to 20 degrees from the Sun, as seen from Earth. That's closer than most observers are comfortable working with, even with proper equipment. For reference, your fist held at arm's length covers about 10 degrees of sky, so the comet will be about 2 fist widths from the Sun, close enough that the glare and brightness of the sky make observation extremely difficult. Professional observatories have special instruments called coronagraphs designed to block the Sun's light and allow observation of objects near the solar disk. The SOHO spacecraft, orbiting in space, carries coronagraphs that can observe comets passing very close to the Sunday. These space-based instruments may capture images of Comet Wierzchos during its perihelion passage, revealing the comet at its moment of maximum activity without the interference of Earth's atmosphere or the challenges of ground-based observation near the Sunday. There's also a geographic advantage for some observers. The Southern Hemisphere, particularly locations in Australia, South Africa, and South America, will have somewhat better viewing geometry during perihelion. From those locations, the comet might be observable in the dawn sky before sunrise, rising above the horizon before the Sun does, giving a brief window where the sky is dark enough to see the comet, but the Sun hasn't yet risen to flood the sky with light. It requires careful planning, a clear eastern horizon, and probably binoculars or a telescope, but for dedicated observers in the right locations, perihelion observations from the ground might just be possible. What scientists hope to see during this critical period goes beyond just pretty pictures. They want to measure the thermal emission from the nucleus itself, determining its temperature and how quickly that temperature changes as the comet rounds the Sunday. They want to track the production rates of different gas species, seeing which volatiles sublimate most strongly and how the ratios between different molecules evolve. They want to watch for any signs of fragmentation or structural failure in the nucleus, any indication that the comet is breaking apart under thermal and tidal stress. Tidal stress, in this context, doesn't mean ocean tides, but rather the gravitational forces acting on the comet. Even though the comet's nucleus is small, the Sun's enormous gravity pulls slightly more strongly on the side of the nucleus facing the Sun than on the far side. For most comets, this differential force is negligibly small, but for comets passing very close to the Sun, it can contribute to structural stress. Combined with the thermal stress from uneven heating and the mechanical stress from gas pressure building up inside the nucleus and erupting through vents, these forces can be enough to crack or shatter a weakly bonded comet. So far, as of the days leading up to perihelion, Comet Wierzchos appears to be holding together well. Observations show steady activity without the sudden flares or dramatic changes that would indicate fragmentation. The nucleus seems solid enough to withstand the perihelion passage intact. But the real test comes in these hours around closest approach, when the heating and stress reach their maximum. There's something profound about this moment that goes beyond the scientific data. For millions of years, this chunk of ice has existed in frozen silence at the edge of the solar system, essentially unchanged since it formed. Now, in the span of a few hours, it's experiencing more change, more activity, more loss of mass than during all those millions of years combined. It's a reminder of the Sun's power, of the enormous energy our star radiates constantly, enough to boil away ancient ice even at distances of tens of millions of miles. It's also a reminder of how dynamic our solar system really is. We tend to think of space as empty and unchanging, but reality is far more interesting. Objects are constantly in motion, falling toward the Sun or swinging around it, evolving and changing. Comets make those changes visible, dramatic, beautiful. They take the abstract concepts of orbital mechanics and solar radiation and turn them into glowing displays that we can observe and appreciate. Right now, as January 20 approaches, as you're watching this video, Comet Wierzchos is in the midst of its perihelion passage, or has perhaps just completed it. The ancient ice is experiencing solar fire. The transformation is happening, and while most of us can't observe it directly from our backyards, we can appreciate what's occurring, understanding the physics and the poetry of this cosmic encounter. The comet has travelled so far and for so long to reach this moment. And now, having reached perihelion, having survived the closest approach to the Sun, it begins the next phase of its journey, the long retreat back toward the outer darkness. But before it leaves entirely, we'll have another chance to see it, a better chance than perihelion offered. The comet still has one more gift to give us. To truly appreciate what happens to Comet Wierzchos during perihelion, we need to understand the physics of the transformation, the intricate dance between solar energy and ancient ice that creates the spectacular phenomena we associate with comets. Start with the comet's nucleus, the actual solid body at the heart of all cometary activity. Think of it as a loosely packed snowball, but instead of just water ice, it contains multiple types of frozen volatiles. Water ice, certainly, but also carbon dioxide ice, carbon monoxide ice, methane ice, ammonia, ice, and traces of many other frozen compounds. Mixed throughout this ice are dust particles, bits of rock and organic materials, along with more complex compounds that don't sublimate easily. This nucleus has been frozen solid for billions of years, cold enough that even the most volatile ices remain stable. But as it approaches the sun, sunlight begins warming the surface. Initially, when the comet is still far from the sun, that warming is gentle, barely raising the temperature above what it was in the Oort Cloud. But as the distance decreases, the heating intensifies dramatically. Remember, the intensity of sunlight follows an inverse square law: halve the distance, and the intensity quadruples. As the comet moves from Earth's distance to half that distance to a third, the solar heating accelerates rapidly. When the surface ice reaches the temperature at which it can sublimate, different for each type of ice, but generally between about -150 degrees Fahrenheit for carbon monoxide to 32 degrees Fahrenheit for water under Earth atmospheric pressure, though without pressure, the sublimation temperature for water ice is actually much lower. The solid ice transitions directly to gas. This phase change requires energy, called the latent heat of sublimation, which comes from the absorbed sunlight. Here's the fascinating part. The sublimation process actually cools the surface. Think about sweating on a hot day when the water evaporates from your skin. It takes heat with it, cooling you down. The same principle applies to the comet. As ice sublimates, absorbing energy to make the phase transition, it carries that heat away in the form of gas molecules moving at high speed. This creates a cooling effect that protects the nucleus from heating up as much as it otherwise would. Without this sublimation cooling, the surface of the comet during perihelion would heat to temperatures hot enough to melt rock. With the cooling effect, the temperature stays closer to the sublimation point of the dominant ice, probably somewhere around the freezing point of water during perihelion, maybe somewhat higher. The comet, in effect, keeps itself relatively cool by boiling away its own substance. But the process isn't uniform across the surface. The side facing the sun receives intense heating and sublimates rapidly. The sides and back of the nucleus receive less direct sunlight and sublimate more slowly, and any areas shadowed by surface features, or facing away from the sun entirely, may not sublimate at all. This creates enormous temperature differences across the nucleus, potentially several hundred degrees between the sunlit and dark hemispheres. These temperature differences create stress. Materials expand when heated and contract when cooled. Different materials expand at different rates. The ice matrix in the nucleus isn't a uniform crystal, but rather a complex structure with varying compositions and densities. As one area heats and another stays cold, stress builds up at the boundary. If the stress exceeds the structural strength of the material, cracks form. You can think of it like taking a glass dish from the freezer and putting it in a hot oven. The rapid temperature change creates stress that can shatter the glass. Comet nuclei, thankfully, aren't usually as brittle as glass, but the principle is similar. Some comets, especially those passing very close to the sun, do fragment from thermal stress. Others develop visible cracks and fissures that become preferred pathways for gas to escape, creating the jets we observe. The gas escaping from the nucleus carries dust along with it. As the ice sublimates, it releases the dust particles that were embedded in the ice matrix. These particles, typically microscopic, ranging from sizes smaller than smoke particles to perhaps the size of sand grains, are carried away by the flow of gas, which can reach speeds of several hundred miles per hour as it accelerates away from the nucleus. Once freed from the nucleus, these dust particles are on their own. The comet's gravity is far too weak to hold them. A comet nucleus typically has escape velocity measured in just a few miles per hour, far less than the gas velocity. The particles drift away, forming the dust coma and eventually the dust tail as sunlight pressure gradually pushes them away from the sunday. Meanwhile, the gas molecules that sublimated from the ice undergo their own transformation. Solar ultraviolet light is intense this close to the sun, and it has enough energy to break apart molecules and strip electrons from atoms, creating ions. Water molecules get broken down into hydrogen and oxygen. Carbon dioxide becomes carbon and oxygen ions. These charged particles interact with the solar wind, the stream of charged particles flowing outward from the sun at about 1 million miles per hour. The solar wind carries a magnetic field with it, frozen into the flow. When the ions from the comet encounter this magnetic field, they get caught up in it, dragged along by the solar wind, creating the ion tail that points exactly away from the sunday. The interaction between the comet's gas and the solar wind can create visible structures, kinks and disconnection events, where the magnetic field lines break and reconnect, sometimes appearing as though the ion tail breaks off entirely and a new tail forms. It's a dynamic, constantly changing interaction. All of this activity reaches its peak during perihelion. The gas production rate can increase by factors of 10 or even 100 compared to when the comet was farther from the sunday. The comet is, quite literally, boiling away, losing mass at a rate that would destroy it entirely if maintained for more than a few days. But perihelion is brief. The comet swings around the Sun and begins its outward journey. And as the distance increases again, the heating decreases, the sublimation slows, the activity winds down. For Comet Wierzchos specifically, observations during perihelion will reveal exactly how vigorously it responds to maximum solar heating. The measurements of gas production rates will tell scientists about the composition of the ice and the structure of the nucleus. If certain gases are detected in particularly high abundance, that provides clues about where in the solar nebula the comet formed and what conditions were like there. If the comet brightens more or less than expected, that tells us about the ratio of ice to dust in the nucleus and how efficiently the surface sublimates. There's also the possibility, unlikely but always present, of something dramatic happening. If the thermal stress is too great, the nucleus might crack or fragment. If a large pocket of highly volatile ice suddenly gets exposed to sunlight, the comet might undergo an outburst, brightening suddenly as that ice rapidly sublimates. These events, when they occur, provide invaluable scientific data because they reveal the interior structure and composition of the nucleus, information that's otherwise hidden beneath the surface. So far, through the approach to perihelion, Comet Wierzchos has behaved predictably, steadily increasing in activity without any dramatic surprises. That's actually reassuring. It suggests a relatively robust nucleus that can withstand the stress. But the monitoring continues through perihelion and beyond, watching for any changes that might reveal something unexpected about this ancient visitor. What we're witnessing is one of nature's most fundamental processes, the interaction between energy and matter, between solar radiation and frozen volatiles. It's the same physics that drives the water cycle on Earth, that creates clouds and rain, that shapes our weather and climate. But on the comet, it's happening in an environment utterly different from Earth, in the vacuum of space, with materials that have been preserved in an unchanged state for billions of years. The transformation of Comet Wierzchos during perihelion is a reminder that our solar system is an active, dynamic place, where ancient materials still respond to the sun's energy in dramatic and beautiful ways. And it's happening right now, in these days around January 20, as the comet makes its closest approach, as the ancient ice experiences the full force of solar heat, as transformation reaches its peak. Soon, very soon, that transformation will begin to reverse. The comet will move past perihelion, beginning its outward journey. But before it retreats too far, before it becomes too faint to observe easily, there will be another opportunity, a better opportunity, for many observers to see this remarkable visitor. Having survived its closest approach to the Sun, having endured the maximum heating and stress, Comet Wierzchos now begins the second half of its journey through the inner solar system, the retreat back toward the outer darkness. But this phase of the journey holds its own points of interest, and for many observers, the best viewing opportunities still lie ahead. Immediately after perihelion, on January 21 and the following days, the comet remains highly active. The nucleus is still hot, still releasing gas at elevated rates, even though the solar heating is gradually decreasing as the distance increases. There's thermal inertia at work just as Earth's hottest temperatures come in July and August, weeks after the summer solstice when days are longest. The comet's maximum activity may persist for a day or two after perihelion, as the heat that penetrated into the nucleus continues to drive sublimation from deeper layers. During these days, immediately post-perihelion, the observing geometry from Earth gradually improves. The comet is moving away from its close angular proximity to the Sun, making it easier to observe without the overwhelming glare of direct sunlight nearby. For observers in the southern hemisphere, the comet becomes increasingly accessible in the pre-dawn sky, rising earlier before the Sun each morning, visible against a darker sky. By late January, the comet has moved far enough from the Sun, as seen from Earth, that northern hemisphere observers begin to get their chance. The comet appears in the eastern sky before dawn, climbing higher as the days progress. While it's gradually fading as the distance from the Sun increases and the activity level drops, it's still active enough to be a worthwhile target for amateur astronomers with binoculars or small telescopes. But the really significant date for Earth-based observation is the 17th of February 2026. On this date, Comet Wierzchos makes its closest approach to Earth, passing at a distance of about 94 million miles. That's not particularly close in absolute terms, still about 140 times farther away than the Moon, but it's close enough that the comet appears brighter and larger in our sky than at most other points in its orbit. The timing is fortunate. By mid-February, the comet will have moved well away from the Sun in our sky, visible in darker conditions without the interference of twilight or solar glare. Northern Hemisphere observers, who had poor viewing geometry during perihelion, now have excellent access. The comet will be visible in the morning sky, rising several hours before sunrise, observable from dark locations with good eastern horizons. For anyone hoping to actually see Comet Wierzchos with their own eyes, this is the opportunity. Bring binoculars or a small telescope to a dark location away from city lights. Look toward the eastern sky in the hours before dawn. Star charts and astronomy apps will show you exactly where to look. You'll be searching for a faint, fuzzy patch of light, possibly with a visible tail extending away from the head of the comet if your sky is dark enough and your optics good enough. It won't be a spectacular sight. This comet never became the bright naked eye object some initially hoped for, but it will be real. You'll be looking at ancient ice and dust from the formation of the solar system, at a visitor that has traveled billions of miles to be visible in our sky, at material that has remained essentially unchanged for 4.5 billion years. There's something profound about making that connection, about seeing it with your own eyes, rather than just reading about it or seeing pictures online. Astrophotographers will have wonderful opportunities during this period. Long exposure images with tracking cameras can reveal the comet's full structure, the coma, the tail, perhaps even jets or streamers in the tail, showing structure in the dust distribution. Every image, whether from professional observatories or amateur backyard telescopes, adds to the scientific record and captures this particular moment in this particular comet's journey. But even as we observe it during its closest approach to Earth, Comet Wierzchos is already on its way out of the inner solar system. The comet passed perihelion on January 20, meaning it's now on the outbound leg of its orbit. With each passing day, it moves farther from the Sunday. The heating decreases. The sublimation slows. The activity level gradually drops. The coma contracts. The tail shortens. The comet is returning to dormancy. By March and April 2026, the comet will have moved beyond Mars's orbit, retreating into the asteroid belt and beyond. The sunlight there is less than half as intense as at Earth's distance, not enough to drive vigorous sublimation of water ice. The comet dims rapidly as both the distance from the Sun and the distance from Earth increase. By late spring, it will have faded below the limit of visibility for all but the largest telescopes, becoming once again a faint point of light, detectable only by professional instruments. Through the summer and fall of 2026, astronomers will continue monitoring the comet as long as it remains detectable, tracking its outbound motion, measuring its continuing fade. Each observation adds to the scientific understanding of its orbit and behavior. By the end of 2026, the comet will be so faint and distant that even major observatories will have difficulty detecting it. It will have returned to obscurity. And then comes the question, will it return? Will Comet Wierzchos, having completed its swing around the Sun, head back to the Oort Cloud for another multi-million-year orbit before returning again? Or will something different happen? The answer lies in the comet's orbit, specifically its orbital energy. Orbits can be categorized by their eccentricity, a number describing how elongated they are. A circular orbit has eccentricity 0. An elliptical orbit has eccentricity between 0 and 1. The closer to 1, the more elongated the ellipse. But there are also parabolic orbits, with eccentricity exactly 1, and hyperbolic orbits, with eccentricity greater than 1. Objects on elliptical orbits are bound to the Sun. They'll always return eventually. Objects on hyperbolic orbits have enough energy to escape the Sun's gravity entirely. They'll leave the solar system forever, never to return. The distinction matters enormously for understanding a comet's fate. For Comet Wierzchos, early orbital calculations suggested an orbit right on the boundary between elliptical and hyperbolic, with eccentricity very close to 1. This meant uncertainty about the comet's ultimate fate. Would it return, or would it leave forever? As more observations accumulated, the orbit became better determined. The current best estimates suggest the comet is on a slightly hyperbolic orbit, meaning it has just barely enough energy to escape the solar system. After its outbound journey through the planetary realm, after it passes beyond Neptune and enters the region where the Sun's gravity weakens dramatically, Comet Wierzchos will keep going. It will leave our solar system entirely, becoming an interstellar wanderer. If those calculations hold up, this visit to the inner solar system is both the first and the last. The comet will never return. Humans will never see it again. After traveling for millions of years to reach us, spending just a few months in our neighborhood, it will depart forever into the vastness of the galaxy. There's something bittersweet about that realization. We're privileged to witness this visitor during its brief passage through our neighborhood, but we're also watching it leave permanently. The observations we make now, the data we gather, the images we capture, these become not just scientific records, but also farewell documentation, the only evidence that this particular cosmic visitor ever passed this way. Of course, there's some uncertainty in that calculation. Orbital determinations are never perfectly precise, especially for objects as affected by non-gravitational forces as comets. The jets of gas erupting from the nucleus create tiny thrust effects that alter the orbit slightly in ways that are difficult to predict precisely. It's possible that more refined calculations, incorporating observations from the entire apparition, might change the conclusion about whether the orbit is truly hyperbolic or just barely elliptical. But either way, if Comet Wierzchos does return, it won't be for tens of thousands of years, at minimum, possibly millions. No human alive today will see it again. In that sense, we're saying goodbye regardless. As the comet fades from view through 2026, as it retreats past Jupiter's orbit and into the outer solar system, we're watching the end of a story millions of years in the making. The ancient wanderer is returning to the darkness from which it came, carrying with it the heat and light it absorbed during its brief visit to the inner solar system, heading back out into the cold and silence. But the story doesn't end there, because even as this particular comet departs, it leaves behind knowledge, insights, and inspiration that will persist long after the comet itself has vanished from our view. You might be wondering why we invest so much time and effort studying objects like Comet Wierzchos. Why do observatories around the world point their instruments at a relatively faint comet that most people will never see with their own eyes? Why does a small chunk of ice from the edge of the solar system deserve this much attention? The answer connects to some of the most fundamental questions we can ask about our existence. Where did we come from? How did our solar system form? What are the building blocks that eventually led to planets, to life, to us? Comets are time capsules. When Comet Wierzchos formed 4.5 billion years ago, the solar system was a very different place. There was no Earth yet, at least not as we know it, no moon, no life. Just a vast disk of gas and dust swirling around the newly formed sun, with materials condensing and accreting, gradually building the objects we see today. In the warm inner regions of that disk, close to the sun, only rock and metal could remain solid. Water and other volatile compounds existed as gas, too hot to condense. But farther out, beyond what astronomers call the frost line, the temperature dropped low enough for water to freeze. There, ice could exist alongside rock, and the combination of rocky materials and abundant ice allowed much larger objects to form. That's why the giant planets are so massive. They had access to far more building material than the rocky inner planets. The comets formed in this outer region as well, or possibly even farther out in what would become the scattered disk and Oort Cloud. They condensed from the same materials that built the giant planets, but they remained small, never accumulating enough mass to become planets themselves. And because they stayed small and cold, because they never underwent the intense heating and differentiation that larger bodies experienced, they preserved their original composition essentially unchanged. Think about what that means. The ice in Comet Wierzchos has been frozen continuously for 4.5 billion years. The molecules locked in that ice are the same molecules that existed in the solar nebula when the planets were forming. The ratios between different isotopes, variations of elements with different numbers of neutrons, remain exactly as they were in the original material. Comets are samples of the raw ingredients from which our solar system was built, preserved in a natural deep freeze, waiting for us to study them. When we analyze the composition of a comet, we're learning what materials were available during the formation epoch. The James Webb Space Telescope observations of Comet Wierzchos, for example, detected carbon dioxide, water vapor, methanol, formaldehyde, and various other compounds. Each detection tells us something about the chemistry of the early solar system. The relative abundances of these compounds help us understand the temperature and pressure conditions where the comet formed. The isotope ratios reveal information about the original materials from which the solar nebula itself condensed. Some of those materials have direct relevance to Earth and to life. Water, obviously our oceans came from somewhere, and while some of Earth's water might have been present in the materials that accreted to form our planet, much of it may have been delivered later by comet impacts during the heavy bombardment period billions of years ago. Every time we measure the isotope ratio of hydrogen in comet water and compare it to Earth's ocean water, we're testing that hypothesis, determining whether comets could indeed have been the source of our oceans. Organic molecules matter too. The complex carbon-based compounds detected in comets, including amino acids and other biomolecule precursors, demonstrate that the building blocks of life existed in the solar nebula before Earth even formed. Comet impacts on the early Earth would have delivered these organic materials to the surface, possibly contributing to the inventory of compounds from which life eventually emerged. We might owe our existence, in part, to ancient comets like Wierzchos. But the importance goes beyond just understanding Earth's history. Every comet we study teaches us about planetary system formation in general. We now know that planetary systems are common around other stars. We've found thousands of exoplanets, and many of those systems likely have their own comet clouds analogous to our Oort Cloud. The processes we observe in our solar system, including comets delivering volatiles to inner planets, probably occur in other systems as well. Understanding our comets helps us understand what might be happening around other stars, perhaps even in systems where life is emerging on distant worlds. There's also the practical consideration of future space exploration. Several space missions have visited comets up close, including the Rosetta mission that orbited Comet 67P, Churyumov-Gerasimenko, for 2 years and even landed a probe on its surface. These missions revealed incredible detail about comet structure and composition, but they're expensive and rare. We can't send spacecraft to every comet we want to study. That's where observations from Earth and from space-based telescopes become invaluable. Every comet we observe adds to the database of comet properties. We learn which characteristics are universal and which vary from comet to comet. We discover the range of possible compositions and behaviors. And occasionally, we identify particularly interesting targets that might be worth visiting with future missions. In fact, there's a mission currently in development called Comet Interceptor, a European Space Agency project designed to visit a pristine comet on its first entry to the inner solar system. The spacecraft will launch and then wait at a gravitationally stable point in space until an appropriate target is identified. When astronomers discover a suitable comet, Comet Interceptor will maneuver to intercept it, performing a high-speed flyby and gathering data from multiple angles using several smaller probes. Comets like Wierzchos help mission planners understand what Comet Interceptor might encounter. The observations inform predictions about activity levels, dust production, gas composition, all factors that affect mission planning and instrument design. The more we learn about long-period comets through Earth-based observations, the better prepared we are to study them up close with spacecraft. There's also the human element, the cultural and historical significance of comets. For thousands of years, humans have watched comets appear in the night sky and wondered what they meant. Ancient civilizations saw them as omens, sometimes auspicious, often frightening. Medieval Europeans feared comets as harbingers of plague and war. It wasn't until the scientific revolution that we began to understand comets as natural objects following predictable orbits, not supernatural signs. That shift in understanding, from supernatural omen to natural phenomenon, represents one of humanity's great intellectual achievements. Edmund Halley's prediction in the early 1700s that the comet of 1682 would return in 1758, and its actual return on schedule, though after Halley's death, provided powerful validation of Newtonian physics and the idea that the heavens follow understandable natural laws. Every comet we study today stands on that foundation, reminding us of the power of scientific inquiry to replace fear and superstition with knowledge and wonder. And there is wonder in abundance. Think about the journey Comet Wierzchos has made. It formed billions of years ago in a cloud of gas and dust surrounding the infant Sunday. It was flung outward by gravitational interactions with the forming giant planets. It spent millions of years in frozen dormancy at the edge of our solar system. Something disturbed its orbit, sending it falling sunward. It travelled for thousands or millions of years across interstellar distances. It entered the inner solar system, transforming from frozen darkness to active glowing splendor. And now it's departing, possibly forever, carrying its secrets back out into the cosmos. We happen to be here, with our telescopes and our curiosity, at precisely the moment when this ancient visitor passed through our neighborhood. We captured its light, we analyzed its composition, we told its story. In the vast sweep of cosmic time, we intersected with this particular comet for a brief moment, and we made the most of that opportunity. That's true for every comet, every asteroid, every astronomical object we study. We're living in a remarkable era when we have the technology to observe the universe in extraordinary detail, to analyze light from distant objects, and decode what it tells us about composition and motion and history. We can watch cosmic events unfold in real time, gathering data that previous generations could only dream about. Comet Wierzchos is one object among millions, one story among countless others playing out across our solar system and beyond. But each object matters. Each observation contributes to the larger picture. Each discovery adds another piece to the puzzle of how our cosmic neighborhood works, how it formed, how it changes over time. And sometimes, the most valuable thing these studies give us isn't just scientific data, but perspective, the realization that we're part of something vast and ancient and ongoing, that the materials in our bodies were forged in stars and transported by comets, that we're connected through physics and chemistry to everything else in the universe. That perspective, that sense of connection to the cosmos, might be the most important thing comets like Wierzchos offer us. They remind us to look up, to wonder, to ask questions about where we came from and where we're going. They remind us that we live in a universe that's endlessly fascinating if we take the time to pay attention. So here we are, at the end of our journey with Comet Wierzchos, though the comet's own journey continues. In the days around the 20th of January 2026, this ancient visitor reached perihelion, swinging around the Sun at its closest approach, experiencing the full intensity of solar heating, transforming in spectacular fashion from frozen wanderer to active, gas-producing comet. By the time you're watching this video, that moment has likely already passed, and the comet is beginning its outward journey, retreating from the inner solar system toward the outer darkness. For those who followed its discovery back in March 2024, for the astronomers who tracked it through 2025 as it brightened and became more active, for everyone who watched as it approached perihelion, this has been a remarkable experience. Not every comet is a spectacular naked-eye object that dominates the sky, and Comet Wierzchos certainly didn't become that. But it didn't need to be spectacularly bright to be scientifically valuable, to be intrinsically fascinating, to be worth our attention and wonder. What made this comet special wasn't just its brightness or its visibility. It was the story, the millions of years of frozen dormancy in the Oort Cloud, the long fall toward the Sun, the dramatic transformation during perihelion, the possibility that this might be its only visit to our neighborhood before departing forever. It was the opportunity to observe ancient materials from the birth of the solar system, to study the composition of primordial ice, to watch physics and chemistry play out on a cosmic scale. And for those of you who have access to dark skies and a telescope or binoculars, the story isn't quite over yet. Remember that closest approach to Earth on the 17th of February 2026. If you're in the Northern Hemisphere particularly, you'll have excellent opportunities to see the comet in the pre-dawn sky during mid-February. It won't be a bright, obvious object you'll need to know where to look, and you'll need optical aid, but it will be there, visible, real, accessible. There's something special about seeing a comet with your own eyes, rather than just looking at photographs online. Photographs are beautiful and scientifically valuable, but they're mediated through cameras and screens. When you look through binoculars or a telescope and see the fuzzy glow of the coma, the faint streak of the tail, you're receiving photons that traveled across millions of miles of space from ancient ice and dust. You're connecting directly with that visitor from the edge of the solar system. It's an experience worth having if circumstances allow. But even if you don't get to observe Comet Wierzchos visually, you've been part of its story by learning about it, by understanding what it represents and why it matters. That's valuable too. We don't all need to be professional astronomers to appreciate the cosmos. We just need curiosity and willingness to learn. And the cosmos will continue to provide opportunities for wonder. Comet Wierzchos is just one visitor among many. In 2026 alone, there will be other comets to observe, some discovered years ago and returning on predictable schedules, others discovered only months before their perihelion passages, fresh visitors from the Oort Cloud making their first appearance in the inner solar system. The comet hunters are always watching, always searching, and they're finding new objects regularly. Beyond comets, there are countless other astronomical phenomena to explore and appreciate. Meteor showers, when Earth passes through debris streams left by comets, creating shooting stars as dust particles burn up in our atmosphere. Eclipses, when the moon passes in front of the sun or Earth's shadow falls on the moon, events that have fascinated humanity for thousands of years. Planetary alignments, when multiple planets appear close together in our sky, gathering for a celestial conference. The ongoing discoveries of exoplanets around other stars, each one a potential world that might harbour conditions suitable for life. Amateur astronomers play a vital role in many of these observations. You don't need a professional observatory to contribute meaningfully to astronomical knowledge. Countless comets have been discovered by dedicated amateurs scanning the sky with modest telescopes. Variable star observations, asteroid tracking, meteor shower monitoring, all these areas welcome contributions from anyone with clear skies and persistence. Even if you don't have equipment or particularly dark skies, you can participate in the appreciation of cosmic events. Astronomy apps and websites provide real-time information about what's visible tonight, where to look, what you might see. Educational content, including videos like this one, brings the universe to your screen, making the cosmos accessible regardless of your location or circumstances. What matters is maintaining that sense of wonder, that curiosity about the universe beyond our immediate surroundings. It's easy to get caught up in daily concerns, to forget to look up, to lose touch with the larger context in which we exist. But the universe is always there, always active, always offering new phenomena to observe and contemplate. Comets like Wierzchos remind us of that larger context. They remind us that our solar system is ancient, dynamic, full of objects that have stories spanning billions of years. They remind us that we're connected through chemistry and physics to everything else in the universe, that the atoms in our bodies were forged in stars and transported by cosmic processes we're only beginning to understand. They remind us that we live in a time when we have the knowledge and technology to decode these stories, to learn from these ancient visitors, to place ourselves within the vast sweep of cosmic history. There's also something humbling about comets. Here's an object that has existed for billions of years, that travelled distances we can barely comprehend, that carries materials older than anything on Earth, and it doesn't care whether we notice it or not. It follows its orbit according to the laws of physics and gravity, indifferent to our observations, indifferent to our interpretation. The universe doesn't perform for us. It simply is, following its own rules, unfolding according to natural law. Our privilege is that we can observe and understand. We can measure and analyze. We can decode the messages carried by light from distant objects and learn what those messages tell us about composition and motion and history. We can take the raw phenomena of nature and translate them into knowledge, into understanding, into a growing picture of how our universe works. That capacity for understanding, that ability to look at a fuzzy patch of light in the sky and deduce that it's a chunk of ancient ice from the edge of the solar system, that it's travelling on a specific orbit at a measurable speed, that it contains particular molecules in particular abundances, that's one of humanity's greatest achievements. It's what distinguishes us as a species, this drive to understand, to explain, to decode the universe around us. And every time we study a new comet, every time we analyse a new data set, every time we refine our understanding of how these objects work, we're exercising that capacity. We're doing what humans do best, seeking knowledge, finding patterns, building understanding from observation and reason. So as Comet Wierzchos departs, as it fades from view and begins its long journey back toward the outer solar system and possibly beyond, we can appreciate what we learned from its visit. We gathered data about its composition, its structure, its behavior under solar heating. We added it to the catalogue of known comets, contributing to the statistical understanding of what comets are and how they vary. We watched a piece of ancient solar system history reveal itself, however briefly, and we had the opportunity to witness, to observe, to connect with this cosmic visitor during its passage through our neighbourhood. That's the real gift comets offer us, not just scientific data, though that's valuable, but connection. Connection to the larger universe, connection to deep time, connection to the processes that formed our solar system and everything in it, including us. Connection to the ongoing story of cosmic evolution, of which we're a very small but conscious part. Before we finish, I want to ask you to do something. Tonight, if your sky is clear, go outside and look up. You probably won't see Comet Wierzchos without a telescope, but you'll see the same sky it's travelling through. You'll see stars, some of which might have their own Oort clouds, their own comets, their own planetary systems. You'll see the Milky Way if you're in a dark enough location, our galaxy stretching across the sky, containing billions of stars and uncountable comets and worlds we haven't even discovered yet. And as you look up, remember that we're part of all that. We're not separate from the cosmos, looking at it from outside. We're within it, made of the same materials, following the same laws, participating in the same cosmic story. The iron in your blood was forged in a supernova billions of years ago. The calcium in your bones might have been delivered to Earth by comet impacts. The water you drink shares its origin with the ice in comets like Wierzchos. You are, quite literally, made of star stuff, connected through physics and chemistry to everything else in the universe. That's the perspective comets offer us, if we're willing to accept it. That's why studying them matters. That's why we point our telescopes at these faint, distant visitors and work to understand their stories. Because in understanding them, we understand ourselves a little better. We understand where we came from, what we're made of, how we fit into the larger cosmic picture. If you found this journey fascinating, if you want to explore more cosmic stories like this, subscribe to the channel. There's so much more to discover: other comets, other astronomical phenomena, other insights into how our universe works, and I'd love to hear from you in the comments. Have you ever seen a comet with your own eyes? What's your favourite astronomical object or phenomenon? What would you like to learn about next? Your engagement helps shape what content I create, and I genuinely enjoy hearing your perspectives and experiences. Share this video with someone who might appreciate it. Not everyone thinks about comets regularly, but many people, if introduced to the subject with context and explanation, find them fascinating. You might inspire someone to look up, to wonder, to start paying attention to the cosmos. That's a gift worth sharing. And finally, thank you for spending this time with me, for following this journey from Comet Wierzchos' discovery through its perihelion passage to its eventual departure. Thank you for your curiosity, your willingness to learn, your appreciation for these cosmic visitors. The universe is vast and full of wonders, and every moment we spend trying to understand it is a moment well spent. Clear skies, and may you always find reasons to look up and wonder.